Hello, everyone. Thank you for joining us for today's Deeper Talk seminar. My name is Jared Heiss. I'm the Science Director at SURF. Before introducing our seminar speaker, a few housekeeping announcements. Today's event is virtual. Questions will be answered at the end of the presentation. Raise your hand on Zoom, or you can enter questions in the Q&A button at the bottom of the Zoom screen. Along with all previous Deeper Talk seminar presentations, this talk will be recorded and available to view online at our public website, institute.surf/deepertalks, as well as on our YouTube and Vimeo channels. If you wish to receive a notification for upcoming monthly talks, go to the Connect link at the top of the Institute website. Now it's my privilege to introduce today's speaker. Dr. Kate Scholberg is faculty at Duke University, and her broad research interests include experimental elementary particle physics, astrophysics, and cosmology. Her main specific interests are in neutrino physics. She has long-term involvement in two experiments conducted in Japan, the Super Kamiokande experiment and the T2K Tokai to Kamioka high-intensity beam experiment. She's a member of the DUNE experiment, the Deep Underground Neutrino Experiment, and one of Professor Scholberg's particular interests with DUNE is the detector's sensitivity to huge bursts of neutrinos from core-collapsed supernovae. In addition, Professor Scholberg serves as spokesperson for the Coherent Project, a multi-detector experiment with the primary physics goal of measuring the SEVENS process, coherent elastic neutrino nucleus scattering, using high-quality, high-intensity neutrinos produced at the spallation neutron source at the Oak Ridge National Laboratory in Tennessee. Professor Scholberg is co-founder of SNOOSE, the Supernova Early Warning System. The goals of SNOOSE are to provide the astronomical community with a prompt alert of a galactic core collapse event, as well as to optimize global sensitivity to supernova neutrino physics. The neutrinos are on their way. I also want to mention that Professor Scholberg is an inaugural member of the SURF Science Program Advisory Committee, providing sage advice regarding facilities, support, and experiments appropriate to SURF. I've known Dr. Scholberg for many years now, starting from when I was doing my graduate work on supernova neutrinos. You're in for a treat. Now let's get set to learn how to spot a supernova from deep underground.
Thanks so much, Jarrett, for that introduction, and I'm very excited to talk to you about these things that I really love. So I'm going to talk about giant bursts of neutrinos that can be detected with detectors deep underground from supernovae, and specifically, I want to zoom in on how we can zoom in on the supernova in the sky, actually using the data from deep underground. So first, I'd like to say a little bit about what supernovae are. Say something about neutrinos, which I think this audience are mostly familiar with, and specifically about neutrinos that come from supernovae in giant bursts, how we detect them, and then also how we can actually use them to point back to the supernova on the sky so that astronomers can know where they are. So the definition of a supernova is a gigantic outburst that completely blows up a star, completely turns the star into smithereens. And this is an astronomical event that for a while can be as luminous in photons as an entire galaxy, which actually I was once taken to task by a famous astronomer for saying this. In fact, it's not really as luminous as a normal galaxy, but it's as luminous as a small galaxy. This is something that happens a few times per century per galaxy. So it's not so common to happen in our own galaxy, for example, only a few times a century, but of course it happens quite often over the whole universe. Now here is how supernovae are classified observationally by astronomers on the sky. And this is a funny tweet I saw that says that if astronomers were in charge of naming them, pies would be called type 2 cakes. Astronomers like to call things type 1 and type 2 and so on. Now, different kinds of supernovae are similar in their energy scale. They're both extremely disruptive events. Type 1s and type 2s are, both blow stars up into smithereens, but their physical mechanisms are very different. And type 1a, which is actually famous for cosmology as a kind of standard candle for telling us how the universe is expanding. This is really a thermonuclear explosion where you have a star that accretes matter from its companion, and then that ignites a nuclear explosion. Type 2 is actually what I want to talk about here. This is a gravitational collapse of a star at the end of its life. After a star has finished burning its fuel, it can no longer keep itself up with its own thermal energy, and it will collapse in on itself. And this is the kind of the event that will create what's called a compact remnant, so a neutron star or a black hole. And this gives you an observational event that is a type 2 type in broad brush. There's also some subtypes as well. But the model here is this gravitational collapse, and that makes this very dense matter, which could even be a black hole at the end of a star's life. And this is the kind of event that is a copious producer of neutrinos. When the star collapses, it scrunches to a very high density. That's what creates the neutron star, or maybe black hole. And then the rebound creates an explosion, and the neutrinos come out in huge numbers. Now, this happens not very often on a human timescale. It happens maybe 3, maybe 2 times per century in our local neighborhood. Here's a nice picture of our Milky Way galaxy and some of its nearby galaxies and Andromeda. The galaxy is about 20 kiloparsecs across. Andromeda is in astronomical units 700 kiloparsecs away. And we can see things within about neutrino bursts within about 200 kiloparsecs. And so 20 kiloparsecs is the size here, maybe 10 times more of that. And within that neighborhood of 200 kiloparsecs, we might see just occasional supernovae. So it's not so crazy to have one over your lifetime, but it's something that's not going to happen every day, which in my view makes it important that we are very prepared to gather all the data that we possibly can. Now, neutrinos, I think SURF has Neutrino Day. Everybody knows about neutrinos, I think. These are the neutral partners to the charged leptons. There's 3 families. There's neutrinos and antineutrinos, so really 6 kinds of neutrinos. We know now that they have tiny masses, and they change their flavors, which is actually how we know they have tiny masses, which is a whole other story. And they interact only via the weak interaction in the standard model interactions. We also know they do interact via gravity, but basically we have exchange of W and Z bosons, virtual particles that create the weak interactions. Now, it's called the weak interaction for a reason. This is just to compare similar energy particles and how much they interact with matter. If you take a photon, a gamma ray, which is a famously penetrating energy of photon, gamma rays will penetrate through a lot of matter in the way that we think about them in our everyday lives. And here's the cross section for photon matter interaction. In an MeV range, it's something like 10 to the minus 24 square centimeters. The cross section telling you the probability of interaction for a neutrino in a similar energy range with carbon, so 10 MeV or so, is something like 16 or 17 orders of magnitude smaller cross section. So neutrinos really interact very weakly. And this, for astrophysics, is both a blessing and a curse. The reason it's a blessing is that because neutrinos interact so weakly with matter, they bring information from very deep inside astronomical objects where perhaps very exotic things are happening, such a very dense matter like a core collapse. Photons are trapped. They can't get out. You can't see what's going on, but neutrinos can bring information from deep inside. And so that's the benefit. And this image here is from a Google search of ghosts escaping. So the ghosts can escape and bring information out from inside the dense matter. But the flip side is, the curse part is that neutrinos interact so weakly, so you have to put enormous effort into detecting them. You need very big detectors. Even for a very high flux, you need an enormous detector to see a reasonable number of neutrino interactions. Now, just to give a kind of qualitative sense of why you have huge neutrino bursts from supernova, from core collapse. So of course, gravitational energy turns into kinetic energy and thermal energy when an object falls. If a piano hits the ground, you get turns into kinetic energy when it hits the ground. You get debris, you get heating, you get sound, that kind of thing. Now, when a star falls inward, a whole star, basically the whole core of a star, which is of the order of a solar mass, that gravitational energy of the fall has to go somewhere. And that energy, because neutrinos interact so weakly, the energy can escape via neutrinos. The neutrinos can take energy out. There's all kinds of stuff going on. It's not only weak interactions, everything is going on in the very dense environment after a core has collapsed. But because the neutrino interactions are so weak, they can make off with the energy and take it away more quickly than any other particle can take it away. And so what that means is that almost all, really almost all, it's 99% of the entire binding energy of the protoneutron star is shed in the form of neutrinos within about 10 seconds, in the form of neutrinos and antineutrinos of all flavors. So it's basically divided into 6 flavors, and it all leaks away. And so that's really physically why neutrino bursts are so huge, why they carry so much of a core collapse energy. It's because the neutrinos can't escape. They can make off with the energy. Now, there's still a lot to understand. Now, things have progressed a lot in the past few decades in understanding of actually what goes on in the dynamics of a supernova explosion. This is still, I would say, I said here, not well understood, but it's still, there are many details that are not well understood, but there's still actually quite a lot of progress. But what we actually understand now from very complex supercomputer simulations of the resulting explosion from a core collapse is that neutrinos are intimately part of the process. Even though, of course, they make off with most of the energy and mostly leave, they do interact somewhat. Things are so dense inside a stellar core that, in fact, neutrinos do interact with the matter, and that actually that in fact is known really to couple with the explosion, and we have to understand how neutrinos, how the whole process works and how neutrinos are coupled into that. And the information that we can get from the neutrinos that escape is in the things that we can measure, which is the flavor of the neutrino in principle, the energy of the neutrino, and the time. And so this entire burst of neutrinos happens on a very short time scale. It happens within tens of seconds. And here is an example model. This is not a very recent model, but the newer models have the same general framework, same general outline of what's going on here. So the top plots here are luminosity of neutrinos in 3 different flavors as a function of time. The bottom 3 plots are average energies. And so these energies are something like 10 MeV or maybe a few tenths of MeV, also the same 3 flavors. And these 3 different columns represent different timescales. The first is what's called deleptonization or neutronization. This is when here, so first actually you start off with the neutrinos getting produced as the star falls in. This is when the electrons and the protons actually get squeezed together to make neutrons. This is actually how you make a neutron star, is the electrons and protons combine to make neutrons and electron neutrinos. And so you get a burst of electron neutrinos right at the beginning in this neutronization burst. There's a little tiny amount of time when the neutrinos are trapped. This is a mind-boggling thing, is that the densities are so high that actually for a short period of time, the neutrinos themselves are actually trapped. Then you get this very bright burst of electron neutrinos from the formation of the neutron star. So this is the neutron star being born. In the next second or so, you see lots of interesting things in electron neutrinos. You can actually see a lot of the dynamics of the explosion that are modulating the neutrino flux. So there's interesting stuff going on here. And then finally, over about 10 seconds, you get the neutrinos that will smoothly take all the energy away from the star and cool over about 10 seconds, which of course is very, very short, but longer than the timescale of the actual core collapse. And there's a generic feature here, if you look at the different flavors, is that the muon and tau flavors of neutrinos, which are associated with the heavier leptons, the muon and tau leptons, are higher energy, and that's because they decouple deeper where it's hotter. And so this is a general feature of these models, is that the mu's and taus and their antineutrinos are higher energy than the electron antineutrinos that are hotter in turn than the electron neutrinos, which are the coolest. And so here's another visualization. This is a 2D visualization. This is the energy on the y-axis and time on the same 3 time scales. The first one is a very short time scale, tens of milliseconds after collapse. The second one is about a half a second. The third one is 10 seconds of the cooling. And the top pinkish ones are the electron neutrinos. And here you can see all kinds of exciting stuff going on, this really bright burst in energy and time. And you also see more hotter neutrinos at the beginning, and then it gradually cools off in the other flavors. And so these are the three flavors that we will get out of the collapse. And these ones are actually all mushed together, have very similar spectra. Now here's another model, and here in this case, this is a very massive progenitor. If a progenitor is more massive, what can happen is that when the collapse happens, you get not a neutron star remnant, but an actual black hole. It actually, there's a further collapse to a black hole. And the signature of this, and this would be amazing to see, this is the kind of thing I dream to see, is the actual birth of a black hole in the neutrino flux. What you actually see, it's a very hot flux compared to the other one, but you get a sharp cutoff. All of a sudden, when the black hole is formed, boom, the neutrino flux stops. And so this would be a really exciting signature to see, where you could actually see the black hole being formed in the neutrino flux in real time. And so that's I think would be a really amazing thing to see. And it's not really understood what fraction of core collapses actually turn into black holes. It's not 0, it's not 100%, and actually nobody really knows what that fraction is. Okay, now there was one example observed of neutrinos from a core collapse, and this was actually not in our galaxy, but a little bit outside our galaxy. Our galaxy is it's about 10 kiloparsecs to the center of the galaxy, and so 5 times farther away, there's a small galaxy called the Large Magellanic Cloud, and there was a famous supernova in 1987A that was seen visually, and from this supernova, there were, in fact, 24 neutrinos observed in 2 detectors, one in Japan and one in the US. And so this is a very famous event. This is what the neutrinos look like. There were a couple dozen neutrinos that have all been scrutinized individually. They were all almost, or very likely almost all, electron antineutrinos, and we'll see why in a little bit. And they were seen about 2.5 hours before the first light of the supernova appeared. And this was kind of generally what we would expect. It's a big, confirms the big picture. But of course, it's only a couple dozen events, a couple dozen neutrino interactions. And so that, of course, leaves many, many questions. There have been many, many more papers than neutrinos written about this burst. But of course, we need more. We're hungry for more data. And what we'll learn from the next burst that's observed is really kind of in 2 categories. We'll learn about the astrophysics, about the core collapse physics, how the explosion works, how the star cools, in fact, whether exotic matter can form. If a black hole forms, we'll see all kinds of other interesting things about the astrophysics and the environment. But we can also learn about neutrino physics. We can learn about the properties of neutrinos from this big old neutrino source. There's actually many things about neutrino oscillation, looking for actually beyond the standard model physics, if there's extra energy that is observed in the flux that is not, or energy that's missing that could go into other kinds of new physics. And so there's, and this is kind of a virtuous cycle in the sense that if we have more information from observations from astronomers, that gives us a better handle on the neutrino physics. And if we have more knowledge about the neutrino properties, that allows better extraction of the astrophysics. And then there's one more thing. It's because the neutrinos emerge promptly that we can use them to alert astronomers that something is going to happen. The delay, I'll say more about this in a bit, but the delay is such that we can actually use the neutrinos to tell astronomers that, hey, something is up, a star has just about to blow up, and you better go look for something. Okay. Okay, let me talk a little bit about how we actually see the neutrinos. So neutrinos interact with matter really in the standard model in 2 ways. You can have a charge current reaction where the neutrino produces a lepton that has the same flavor as the neutrino flavor. So if it's an electron neutrino, it makes an electron. If it's a muon neutrino, it makes a muon. But you have to have enough energy. The neutrino has to have enough oomph because of mass energy conservation. You have to, if you're going to create a particle in the final state, there must be enough energy to create that particle's mass. And so that means that if you are a muon neutrino, you actually need 100 MeV or more than 100 MeV to actually create a muon. And so that means that if you're a muon neutrino, you can't interact. If you've only got 10 MeV, like if you're from a supernova, you actually can't make a muon, and so you're actually invisible, except if you have a neutral current interaction, which doesn't care about the flavor. And so this is an important thing to understand about how neutrinos interact with matter. Now, in the energy range we're talking about, so up to maybe several tens of MeV, maybe up to 100 MeV, these are the interactions that are relevant. Neutrinos can interact with they interact with particles in matter, so they can interact with atomic electrons by scattering. So neutrino just comes in, smacks an electron, the electron zooms off. And actually this I'm going to come back to because the electron remembers the direction it was kicked in, and so that actually turns out to be useful for figuring out where the supernova is. The next simplest target is a proton. And if you have for example, water, which has free protons, you can have an interaction of an antineutrino on a proton that makes a positron and a neutron. And you can see the positron and actually sometimes see the neutron as well. You can also have a neutral current interaction, which doesn't care about the flavor or the neutrino just comes in and smacks the proton, but it's a bit like hitting a bowling ball with a ping pong ball. That is actually easier to do than hitting an electron, but the bowling ball will, if it's a proton, it's like a bowling ball, it will roll off with only a little bit of energy. So you tend to get only a little bit of energy in the final state. You can also have an interaction with an entire nucleus. So where a neutrino will interact with a nucleus, it will change the nature of a nucleus. It will change a proton to a neutron or a neutron to a proton. And this is something where you can see then the electron or positron in the final state. Sometimes there's other debris that comes out. You can also have neutral current interaction where you excite the nucleus, the neutrino comes in, you get some gammas that come out and see those gammas. You can also have what's called sevens, where you have the entire nucleus recoils, and if the proton is like a bowling ball, the nucleus is like a boulder, and so this is actually really only very, very tiny recoil energies. And this one is really the big one, the inverse beta decay on protons, where it's antineutrinos that are interacting is what is dominant for current detectors. So these are the detector types that we have for supernova neutrinos, and these are mostly made of materials that have a lot of free protons, and so they're mostly sensitive to electron antineutrinos. So we have big water detectors. I'll say a bit more about all of them. Scintillator is hydrocarbon. Argon is interesting because it's especially sensitive to electron neutrinos. You can have an interaction with an argon nucleus, which is primarily a filter for electron neutrinos. And then there's some others as well. Other detectors that are built for dark matter are sensitive to the coherent scattering. So something where it's sensitive to all the flavors of neutrinos. And there's one instance of a lead-based detector that's at Snow Lab in Canada. And these are all detectors. They pretty much mostly have day jobs. They're mostly built for other things other than supernova neutrino detection. But supernova, if there is a supernova and a burst of neutrinos, they can do a fantastic job on observing the burst. So let me talk about some of these in broad brush, some of these detectors. So water Cherenkov detectors are basically big tanks of very clean water, and the way you see the neutrino is from Cherenkov radiation of the charged particle that's produced. And so if you have inverse beta decay, you have a positron in the final state, and this will create a kind of shock wave of light, will create a ring of Cherenkov light, which then the photons can be observed on photomultiplier tubes that are covering the inside of the vessel. And this is a interaction. It's very widely used for many purposes in neutrino physics. And the main current instance of this class of detector is the Super Kamiokande detector, which is a giant water Cherenkov detector in Japan. It's actually famous for many things. Neutrino oscillations with beams and atmospheric neutrinos, and solar neutrinos as well. This has 50 kilotons of ultra pure water. It's in a mine a kilometer underground in Japan. You want to be underground to, of course, shield from the cosmic rays. And the inside of the detector is lined with 13,000 very large photomultiplier tubes. Here's some pictures, and this detector is primarily sensitive to this interaction of electron antineutrinos. And if there's a galactic center supernova, there'll be of the order of about 10,000 of these observed in about 10 seconds. And this is an animation that was made by one of my students some years ago. This is actually what it would look like in Super K, what a burst of supernova would look like in real time. And so what this is a projection. It's an unrolled view of a cylinder, and each little dot is one light sensor. And this is the outer detector where it's a kind of veto for cosmic rays. And so when I click here, you're going to see this detector light up like a Christmas tree, and you're going to see the energies of the neutrinos build up. So here, go in here. So this is just noise, bam. So the whole thing goes on. You can see rings. It's all huge rate over 10 seconds of Cherenkov rings everywhere. And in fact, you can get information about the direction, which I'm going to come to a bit, because some of the neutrinos are hitting electrons, which are light targets, and they tell you where the supernova is on the sky. Now, the next generation water detector is called hyperkamikanda. This is something like 8 times bigger than Super K, and would have of the order of 10 times more events, so of the order of 100,000 events. Also, mostly electron antineutrino flavor. So one of the 6 flavors that are coming out, and actually this is, I think, construction has started. The cavern is now finished, and so this is this detector is well underway, which will be a great upgrade to Super K and a huge supernova detector. Another kind of water detector is when you have solid instead of liquid water. There are detectors that are built actually primarily for very high energy neutrinos. So neutrinos of PeV and many hundreds of TeV, so much higher, many orders of magnitude higher energy than supernova neutrinos. And these kind of events actually give these enormous kilometer scale showers of Cherenkov light in the ice. And so IceCube CAM3net is in the Mediterranean, but similar idea. Actually liquid water, not solid water. IceCube is solid. And here you think, well, these are very sparse arrays of phototubes. The phototubes are 10 meters apart. How can you actually see a little teeny 10 MeV neutrino? And the idea is to actually look collectively. For example, in IceCube, if a supernova happens over 10 seconds, there are so many neutrino interactions in the ice that the entire ice glows with Cherenkov light. And the idea of detection is that you track the single phototube glow. You just see single photons from any given event, but the phototubes pick up this statistical glow of all the neutrinos interacting within those 10 seconds. So this is a really a kind of different approach, and also very interesting because it gives you the time profile of the signal. Then there are Cherenkov detector, or not Cherenkov, they're scintillation detectors. These are detectors that are composed of hydrocarbons, so mixtures of carbon and hydrogen and free protons. And these also are sensitive to electron antineutrinos by the same interaction, where instead of Cherenkov light, what you get is scintillation light. That's a material that emits light when energy is deposited in it. And these give lots of light, and so they actually have very good energy resolution. You can make very good energy measurements of the individual neutrinos, but they don't have the Cherenkov pointing. So pointing is much harder in these detectors. And there are many instances of these. Some of these have recently turned off, like Bursino, but there's Camland in Japan, Snow Plus in Canada, and there's even some surface detectors, and an experiment in China called Juno is turning on very soon. And these will have also thousands of neutrinos, mostly electron antineutrinos, if a supernova goes off. Now let me come to DUNE, which of course I think people listening to this are probably familiar with. This is a kind of argon, an argon-based detector, are configured as what are called time projection chambers, where you have a particle energy deposition, you have a high electric field, you drift the charge, and you pick up an image of a track on a collection on planes that will collect information about that charge. And so you can actually, in principle, get very fine-grained images of the final state of an interaction. And you also get scintillation photons as well. And this is very good for seeing electron neutrinos. If you remember, the water and scintillator detectors were mostly sensitive to electron antineutrinos. These detectors are sensitive to electron neutrinos by interaction on the argon nucleus, which produces, with a pretty high cross-section, an electron. And what you can actually see is the track of the electron. And then you get an excited state of potassium, which will spit out a bunch of gamma rays, and you can actually see the signature of those gamma rays as well. And so there's a bunch of instances of this. There's smaller ones at Fermilab. And then DUNE, of course, is the big one planned for the US. And this detector's day job is looking for long baseline neutrinos, so neutrinos that are generated at Fermilab, to understand the oscillation of neutrinos. But it's a fabulous supernova neutrino detector as well. It will have a very good sensitivity to a burst of neutrinos, and we'll see mostly the electron neutrino flux. So it's complementary to the scintillator and the water detectors. And so these three big detectors are the next generation big underground detectors. There's Hyper K made of water, primarily sensitive to Nu bar. There's Juno made of scintillator, primarily sensitive to Nu bar. And then Dune, that is made of argon, which is primarily sensitive to Nu E. And I have to emphasize, these are highly complementary. They see different interactions with different strengths. For instance, Juno, very good energy resolution. Hyper K, good pointing. Dune, electron neutrino flux, and also good pointing, and I'm going to say about. And so these are really, this is not a, it's not a competition. Everybody gets to bring something to the table if there's a neutrino burst. And just to give you some numbers, how many events will we see? This is as a function of distance to the supernova. Here's the galaxy edge at about 20 kiloparsecs. Large Magellanic Line Cloud at about 50, Andromeda about 700. And Super K will see maybe one event from Andromeda, Hyper K, a handful of them. And, so this is basically how far we can see. We can see the whole galaxy with very good statistics with the next generation detectors. And it's really the more than merrier. You want all the flavors, you want all the information. Everybody, it's not a competition. It really is not a competition. Everybody will dine richly if there's a supernova. So now let me talk about the early alert and the pointing. So this is a plot showing different messengers from a supernova. We've talked mostly about the burst of neutrinos, but a supernova also has a high flux of photons, of course. We talked about that. That comes later. And it also has gravitational waves. The photons are actually a lot, even though it's extremely bright in photons, it's still very lower flux in photons. Of course, it's easier to see photons. And that will happen hours or even days after you get the neutrino burst. The gravitational waves also prompt, but actually a fairly uncertain signal. There's a lot of different models. We actually don't quite know exactly what to expect from gravitational waves, but there will probably be something in gravitational waves. And so what you expect from a core collapse is in fact also a pre-supernova. There's a very slow increase and uptick of the fusion generated neutrinos from a supernova before, actually hours or days or even longer before the collapse. Then there's this really bright burst of neutrinos, which cools off only after 10 seconds, coincident with the gravitational waves. And then only later do you get the electromagnetic radiation. And how late do you get the radiation? And this turns out to be very dependent on the type of star. So if it's a star that's mostly naked, doesn't have much envelope, it could be a very brief interval between the core collapse and when you actually see the with the electromagnetic supernova. That would be down here. So very short propagation time. Other stars like Betelgeuse that are red supergiants and have these big bloaty envelopes, these kind of stars might have quite a long delay. It could be hours, it could even be up to a few days before you actually get a shock breakout and a bright supernova. So if we want to use the neutrino burst to alert astronomers to a supernova about to happen, we're really racing the shock. We want to have we have very little time to figure out where the supernova is in order to tell astronomers. Of course, astronomers want to know where to look. I think many of them, of course, want to know even if they don't have a direction on the sky to look, but the more precisely you can point astronomer to where to look for a supernova, the happier they are and the more likely they are to get science out of it. And so the question is, can we use the neutrino signal itself to point? And the answer is yes. I'm going to talk about that. And I also want to mention here that there actually might not be a supernova. I talked about black hole formation, which we could see very clearly in the neutrino signal. It would be a very sharp cutoff, but that is likely to result in no bright event. What that would look like to an astronomer could be a star that was there and then it winked out. And so even if we never find the optical counterpart, it will be useful to use a neutrino direction to look for a star that has winked out, which would be potentially tell us that there was a black hole formed. And another maybe more esoteric thing is that even if we never find an optical counterpart, we can actually use that direction to tell us how the neutrinos propagated through the Earth, which will give us information about neutrino oscillation. So direction information, even if it's late, is better than never. Even if we don't see a supernova in time or don't see a supernova at all, we still want to use the neutrino direction, but the faster the better. So there's actually more strategies, but here are the two main strategies by which we can use the neutrinos themselves to point to on the sky to where the supernova is or would be, or where the collapse happened. One is by an interaction which remembers where the final states remember how they were kicked. And so the canonical example here is you have an electron, it's a light particle. When a neutrino scatters, it actually scatters the electron forward in a cone. That, if you can measure the direction of the electron, then you get information about where the neutrino came from. But of course, you need a detector that tells you the direction of the electron, and you also need to do this. You need to do the reconstruction quickly. Now, another strategy is triangulation, which I think is more, the better technical term is multilateration, but people still say triangulation. And here the idea is to use the relative timing of the neutrino wavefront seen by detectors around the globe in order to infer the direction of the supernova. So this is actually doable, but it's quite hard because the width of the pulse of neutrinos is greater. It's tens of seconds. The transit time across the Earth is much smaller than that. And so that means that you have to have very good statistics in order to sample the timing so that you can actually use that relative timing information. But it's something that's doable. It's just relatively difficult. Now, let me go back to this neutrino interaction to talk about the anisotropies. Like, how can we actually, which of these interactions remember the direction of the neutrino, and how can we make use of that? So we have the charge and the neutral current. And I'm going to sort of talk about them in the context of how well they, how do they look like from the point of view of a neutrino. So you imagine you're a neutrino and you smack into something. What does this look like to you, or how does this feel to you? So if you have a coherent elastic interaction, a sevens, this is an interaction with a whole nucleus. This is the ping pong ball hitting a bowling ball. What does that feel like if you're a neutrino? Well, kind of hurts. You smack into something, but doesn't hurt that much. You don't lose that much energy. Suppose it's something lighter like a proton. If you smack into that, actually that kind of hurts more. You give up more of your energy to that proton. So, there's some information, some energy gets transferred. If you hit an electron, that actually kind of hurts a lot. You don't lose all your energy, but you can lose more energy. So that, bigger ow there if you're in the neutrino hitting the electron. Now, what if you hit the whole nucleus and, just excite it? You can lose a fair amount of energy, and that also hurts kind of quite a bit. If it's a charge current interaction, you actually can give your whole energy to the final state. You're not a neutrino anymore. You get absorbed. And this is, actually gives information. You tragically die, but you leave your full flavor and form momentum legacy in the final state that in principle is observable. And so here's now a picture of the energy distributions that you get for some of these different kinds of interactions. This is what you get, the energy you get in the final state, the observable energy in the final state. The top plot is for argon. And so you get lots and lots of these sevens, where you just barely bump into something if you're a neutrino and you don't leave very much energy. And then you have the charge current interactions where you leave all your energy or in a final state. And that is, much harder spectrum to be able to observe, so easier to observe, but a lot fewer of them. In between is kind of the elastic scattering of electrons. This is the same kind of plot for carbon-based detectors, for scintillator-based detectors, where, again, you've got lots of these very low energy events, only a few high energy ones, and then the elastic scatters are in the middle. Now, if you want to use the information in the final state to figure out what the momentum of the neutrino was, the forward momentum of the neutrino, the detector also has to be capable of exploiting the directionality, and that's hard. Now, I'm going to rate all of these. So the saddest ones are the nuclear excitations. These are actually not well understood, and you just get a bunch of debris that goes off in all directions, and so these are very hard to use for pointing. Elastic scattering off nuclei is actually kind of okay. There is actually a well-defined anisotropy. There's some memory, and you can get a lot of statistics, but it's very hard to track these little teeny recoils in practice. And so this is experimentally hard to do, although there is information. Charge current interactions where you have the full form momentum in the final state. This is okay. And on larger nuclei, you don't necessarily understand the cross-section that well, but it's maybe doable. And the lepton is the easiest thing to see, and that's actually relatively poor anisotropy in many cases, but there's stuff you can do. This is the really good one for pointing, is elastic scattering on electrons, because every detector has electrons. The anisotropy is very well understood. It's forward pointing. It does have a very low cross-section, but if you have a really big detector, you still get enough of these to actually do the measurement pretty well. And this is how, for example, Super K and Hyper K can do it. They have excellent intrinsic directionality. You actually get a Cherenkov cone that is pointing forward in the direction of the electron. And so you can actually use this, for example, in Super K to point back. And so this is a well-known method. And it's well shown quantitatively that, for example, for Super K, it's several degrees pointing for a core collapse at the center of the galaxy. And here you can see this isn't maybe hard. This is the true direction of the supernova. There's an excess in that direction on top of a nearly isotropic background of inverse beta decay. But this is something that can be fit, and is actually with a recent upgrade to Super K, which I don't have time to talk about, will actually get much better, and Hyper K will do very well too. Now, Dune is also capable, because actually very nice tracking of the final state electron. You can actually see exactly where the electron's going. There is an ambiguity because the detectors are slow in picking up the ionization, and so you don't know if an electron is going in one direction versus another direction. It's called a head-tail ambiguity, but this is something that is possible to still resolve. And so here's just some examples. This is from a recent paper on Dune, showing here how the electron elastic scattering is forward pointing. This is energy. This is the direction. Most of the electrons are pointing forward, and we can actually reconstruct that very nicely in a time projection chamber. The background is for the regular charge current interactions, which are, and actually there's interesting side stories, which I don't have time to talk about, but that is a quasi-isotropic, but you can fit that. And so here's an example. This is another animation. Let's see if I can get this to go. Nope, it's not going. This one is not working. Okay, well, you can point really quite well using well understood reconstruction techniques for a detector like Dune. And so we can show that optimistically several degrees competitive with Super K. There's some challenges there in actually disentangling the different types of interaction, but it's actually quite promising for a detector like Dune. And so here is an example. This is just the pointing resolution in degrees as a function of how well you can pick out the elastic scatters from the other events. And it's something where you want more statistics, and the bigger the statistics, the better you do. Oh, here's the animation. I'm sorry. So this is not quite here. So here you go. This is what it would look like on the sky. This is a likelihood map, and you could see over the course of the burst, as more neutrinos come in, you can narrow down the region on the sky to where the supernova is, using this is relatively optimistic assumptions for Dune, but it's something that's quite within the realm of possibility. Okay. All right, and so let me just say a couple things about triangulation or multilateration. This is hard for the reason I mentioned. It's because the burst is spread out over a much longer timescale than the time difference between different detectors, which is several milliseconds. But there's actually quite promising studies that show this is an example of combining several different detectors. You could actually get a region on the sky that is certainly better than not knowing anything. And actually, if you combine that with information about where the supernovae are likely to be on the sky, that actually can do pretty well. And in fact, you can combine everything all together. And just the final thing I want to talk about is this network called SNOOS. This is the supernova early warning system, which is a worldwide network of different detectors around the world. This is the SNOOS 1.0 early version of it, which in this picture now includes experiments that have now completed their missions, but includes some that are still going, such as HALO in Canada, LVD, Super K, CamLand, and IceCube. And this is now an upgrade to this network is underway to SNOOS 2.0 with improved latency, also including the pointing, including the combination of information to make triangulation, and also looking at pre-supernova, which is a true early warning that a supernova is about to happen. And everybody can sign up. Here's the website where you can actually sign up to be on the alert list. And this is we expect to be going live with Snooze 2.0 in the relatively near future. And let me just end with the neutrinos are coming. If you think about it, the far side of the Milky Way is about 650 light centuries away. And about 2,000 core collapses have happened in the middle Milky Way in that time, have happened already and are on their way. So have happened within 650 centuries. And those neutrinos are coming, and eventually the wave fronts of the neutrinos will get to us on the Earth, and we really have to be ready. Okay, so here's my takeaway messages. First, there's enormous information to be had by observing the neutrinos from a core collapse burst. We need to measure the energy and the flavor and the time structure, and that gives us a huge amount of information. The current and near future detectors are sensitive basically to the galaxy. The future detectors, such as DUNE, will have a much richer flavor sensitivity, for example, electron neutrinos and argon, and there's lots of exciting multi-messenger prospects that I haven't had much time to say about, other than to say that there's more out there, and the statistics will be such that we should get even reasonable statistics from Andromeda. And so there's Dorothy looking at looking for the supernova and opening a world to multi-messenger different colors of neutrinos. The directional information is valuable. You need it fast, but late is better than never. The neutrinos can point. We can get information from that. The information from single detectors from the anisotropic interactions where the neutrinos remember or the final state remembers where the neutrinos came from, that's probably the best way of doing it, but multilateration may give us some fast information. And we need to prepare to get as much from the supernova, the next supernova neutrino burst, as we possibly can. So I will stop there.
Wonderful. Dr. Scholberg, thank you very much for explaining how to spot a supernova from deep underground. We can open the talk up for questions, and there's one online. Let me unmute Batash. There we go.
Oh, I see the question. Why
Batash, do you want to? Oh, yeah.
Oh, sorry. Go ahead.
Yeah, so am I audible?
Yep.
Yep.
Thank you for the wonderful talk. I have a couple of questions, if you can take. First of all, in the core collapse supernova regime, you have clubbed together the muon and tau type neutrinos. Why is it so?
Oh, that is a fantastic question and has a very interesting answer. And the reason is it's because you can't have charge current interactions from muon and tau neutrinos that are less than about 100 MeV. It's because for example, in order to make a muon, you need enough energy to make the rest mass of the muon in the final state. And a muon is 106 MeV, and so you need more than 100 MeV of a neutrino to actually do that. And so that means because all the supernova neutrino energies are less than 100 MeV, and actually it's even worse for taus. Taus are 3.5, they're GeV, so their taus are even heavier than that. So you need even more energy to make a tau. And so all of those neutrinos, only if they have the mu's and taus and their antineutrinos, if they have less than 100 MeV, they can only have neutral current interactions. And so they all look the same. Neutral current interactions don't care about the flavor. And so mu's and taus and U bar and U tau bar, they all look the same, both from the point of view of production in the supernova and also from the point of view of detection. And so that's why we put them all together, because they all have, to a very good approximation, exactly the same spectrum and exactly the same detection and cross-section.
I see. Another question of mine was like around the 50 kilometer or 70 kilometer radius of the core, PNS core, the density is so high where the neutrino self interactions become relevant.
Yes.
And there the gravitational wave amplitude has an interplay with the neutrino dynamics.
Yep.
Can you shed some light, there are works like nowadays which says that the enhancement of the gravitational wave amplitude in the current set of detectors. So if we follow the multi-messenger approach, what we can what additional insights we can gain from like doing neutrino as well as gravitational wave approach, because like there have been studies with the electromagnetic counterpart. So I wish to know like with neutrino along with the gravitational waves.
Yeah, no, that's a great question. That there's very likely an enormous amount that can be learned by looking at the combination of a gravitational wave signal and a neutrino burst signal. Actually, in neutrino physics as well as in the physics of the core collapse and so on. You mentioned neutrino-neutrino interactions. That's actually kind of a separate thing that I don't think I said very much about, but that's actually extremely interesting and very lively theoretical study at this time. That actually results having an environment where the interactions of neutrinos with themselves matters that's a mind-boggling thing, if in my view, but
Yeah, so
something that can happen, and that can actually create nonlinear oscillation effects. And actually, that's something where I think the theory hasn't really settled out, and so that can actually give fairly substantial modulations to the flavor content of the signal as a function of time. And so that's a very interesting thing. Now, for the gravitational waves, that's also, I think, something where the theory is there are actually more uncertainties than for the neutrino production. And in fact, which you can think of as an opportunity, that if you actually are able to measure a gravitational wave signal in coincidence with a neutrino one, that can give very great insight into the dynamics of the collapse. So there are many, many very interesting opportunities there.
thank
Yeah,
you.
thanks for those questions.
Thanks. We have another question. Sir, DOE Program Manager, Clayton. Unmute you. Go ahead and ask, Clayton.
Do we have telescopes that are broad enough field of view to capture the whole area that it looks like the neutrino pointing isn't going to give you an extremely precise location? Do we have telescopes that are broad enough to actually watch that whole field?
Yeah, that's another great question. Is the answer is we have, of course, many different telescopes with many different fields of view. Actually, that's part of the point of SNOOS, is to try to connect observers. In fact, it includes amateur observers. Amateur observers actually have very broad access to the sky and great knowledge. And part of the mission of SNOOS is to try to connect amateur astronomers to try to help pinpoint very early light. Of course, as neutrino people, we want to make the area on the sky as small as possible, but we are limited by the physics of neutrinos. The hope is that with a broad array of observers looking as soon as possible, it should be possible to narrow down where the supernova is to enable the really good telescopes to get there as quickly as possible.
Thank you.
Other questions? Or maybe I can ask one.
Go
Oh,
ahead.
one in the chat. Sorry.
There's one in the chat, yeah, that I see.
Oh, go for it, Kate. If you can see
Oh,
that,
it's
go ahead.
Snow Globes. Oh, Snow Globes. Okay, so that's a software package that I have public. It's a public package. Are we able to introduce external smearing matrix? Yes, although I think that particular code is not committed to GitHub. So the answer is in currently not generally. So that's a good thing to add to the list of things to do. It's called Snow Globes. SNOWGLOBES. And it's a package that allows calculation of energy spectra from realistic detectors, observed by realistic detectors for different supernova fluxes and cross-section assumptions.
Maybe I'll throw in, oh, here we go. Yep, good, thank you. You mentioned a suite of different experiments, different detector technologies. The ice cube detector signal is a little different than the others. I don't know if you want to say a bit more on how that would fit into the snooze algorithm.
Yeah, so it is a somewhat different nature of signal because it's not a detector that will reconstruct individual interactions like the others. It's just a kind of statistical excess over background, but it's still that way of measuring will still provide an early alert. I mean, you can I believe IceCube Collaboration and CAM3Net both have early monitor systems set up where they are able to pick up effectively an anomalously large single photon event rate and provide an alert to snooze. So it's you know, it functions perfectly well as a monitor that something is up. The main difference is that it's really just counts over background as opposed to a you know, you can't reconstruct a detailed energy spectrum or anything like that.
One other question I had, the LZ dark matter detector at SURF, is it part of snooze? I know they were hoping to join,
Yes.
have joined. Yeah.
Yes, I think so. That's a good, they're not part of snooze 1. So I'm less involved in snooze 2 than snooze 1 is still running for now, and I'm actually still running that. But snooze 2 is the new incarnation. And I believe there are LZ people in the working group. They're both Xenon and LZ people in the working group. And as for the status of their alert, that I'm not sure I can answer off the top of my head.
I believe they were doing some electronics upgrades to support their involvement or better involvement in snooze. All right, well, we're getting close to the top of the hour. We try to let people break to get to classes and other things. Maybe not classes just yet, but we want to thank you again, Dr. Scholberg, for your fabulous talk. I really enjoyed the animations. I thought that communicated the evolution of the supernova verse really well. Just to wrap up here, the housekeeping, this talk is available to view and share on YouTube and Vimeo, as well as via our public website, institute.surf/deepertalks. Next month's Deeper Talk seminar is scheduled for September 10 at our usual slot of 9 a.m. Mountain Time. The topic, geothermal energy and the CUSP experiment, with featured speaker, Dr. Kevin Rosso. As always, your feedback helps improve the program, and we appreciate any suggestions for speakers and topics for future presentations. Please fill out the short survey, and you'll receive immediately following the talk on Zoom and in your email. Once again, thank you for joining us. Talk again next time.